In this video, we're going to look at the kernel processor in RAMP. But before we start, we will look at what a kernel processor actually is. So, kernel processing is a very common image processing technique that's sometimes referred to by other names, such as kernel convolution, matrix convolution, spatial convolution, or in fact just image convolution. I have a diagram here that I drew to explain how it works. In this big square here, I have an input raster with a series of cell values. And over here, I have my kernel. Now, anything that's highlighted or shown in italics is the terminology that's used in RAMP for describing kernels. So a kernel is essentially a smaller matrix that contains a series of kernel items. In this case, this is a 3 by 3 kernel, and it has a central pixel that's referenced as the 0, 0 pixel. All of the kernel items are specified with respect to the central 0, 0 pixel. Now, each kernel item contains a multiplier. This multiplier, we'll look how that's applied later in the kernel processing. But also a kernel has what we call an inverse scalar. And we'll look at that and how that works later. So essentially the way a kernel is applied to an image is the kernel is placed on top of the image and then periodically moved to the next cell along and the next cell along and the next cell along. So this is a moving window that's applied to the underlying input raster. And as it completes over here, it jumps down to the next row and begins processing that iteratively as well. So let's have a look what these multipliers and the inverse scalar actually do. So in the top left-hand corner of my kernel, I have the original multiplier values that I had that I was showing you over here. So what this does is, this defines a neighborhood about a central pixel in the input raster, and each of those multipliers are applied to the value of the cell. So it would be 1 times 0 is 0, 2 times 2 is 4, etc. All of these resultant multiplied values are then added together. So in this case, you can see I've got it here, and all of the multipliers applied to all of the cells within the kernel area equal a value of 74 in this case. The inverse scalar comes in, this value number here, 16, because I then take the sum of all those resultant values and divide it by 16 to give me a final result of 4.625. Now this is the value that will be applied to the pixel about which the kernel has been applied in the output raster. And so the process continues again and again and again as this kernel moves across the input raster, and we get a result and a new raster that's been filtered based on the kernel. Just going back to the definition of a kernel here, you will notice that the inverse scalar in this particular example is 16. This 3 by 3 kernel is in fact a Gaussian kernel, but we can define kernels to do a whole bunch of different things. And if you're familiar with applying filters in say Photoshop or GIMP, you'll be used to using kernel convolution even if you didn't know you were using it. So common kernels might be a Gaussian blur, a mean blur, edge detection, sharpening. These are all very common kernels that are used in image processing. I just want to make mention of this inverse scalar here. In RAMP, you can define the inverse scalar, and we'll look how you do that later in a custom kernel, but you can define this as 0. And of course, you can't divide anything by 0 without it being an infinite number. So that would normally be invalid. However, in RAMP, if this is specified as 0, the scalar is then calculated as the sum of all the multipliers within the kernel. So in this case, it would be 1 plus 2 plus 1 plus 2 plus 4 plus 2 plus 1 plus 2 plus 1 equals 16 anyway, so it's the same value. So I could have specified 0 here or 16, and it effectively would have been the same thing. Now the advantage of specifying 0 is that if I go back here, say for example this cell in my input raster was in fact null, I wouldn't be able to then take the sum of all these things and expect and divide it by 16 and expect the result to be the same. So if I have an inverse scalar of 0, it actually calculates the scaling value based on the sum of the multipliers that have valid inputs from the raster. So if, for example, the upper left kernel item in this case was null, it would actually sum these values here to give a resultant inverse scalar of in fact 15 in that case. So that's a little bit about how kernels work. Let's look how they look in RAMP. So in RAMP I have a tool here called the Kernel Editor. If I double click on that, it launches the Kernel Editor, and I can load some of the predefined kernels that come with RAMP, or in fact you can define your own kernels, and we'll look at how to do that. Let's look at the 3x3 Gaussian that we just looked at in the graphical example. And here it's showing those values. So the same values we saw, 1, 2, 1, 2, 4, 2, 1, 2, 1. The colors that are assigned to these describe the shape of the kernel. So let's look at and you'll notice actually in this case that the inverse scalar is 0. So that means that it will calculate it based on the sum of the valid multipliers in the kernel. But let's look at it a bit more of a complicated kernel now. Let's look at a Laplacian of Gaussian kernel. So this is a 9x9 kernel. And you can see all the colors here that sort of describe the shape of this particular kernel. The higher values are described are shown in a more yellow color, and the lower and the negative values are shown in a bluey color. I can change that in the kernel editor if I don't like those colors. Let's say the positive values become green and the negative values become red. So this gives me a feel for what the kernel actually looks like. Let's see what a Laplacian of Gaussian kernel might look like in 3 dimensions. So here's a 3-dimensional picture of a Laplacian of Gaussian kernel. And you can see the values here that are tending towards 0 increase slightly and then drop away to these big negative numbers. And we see that in the rendering in the RAMP kernel editor. So hopefully this gives you a feel of how the RAMP kernel editor is trying to describe the general shape of a kernel to you. So let's look a little bit more at the kernel editor before we launch into actually applying kernels to filter imagery in RAMP. I'm going to go and open a simple, do you wish to change? No, I don't want to change, save it. Let's look at a 5x5 Gaussian in this case. Okay, so this is what my 5x5 Gaussian looks like. You'll notice the inverse scalar in this case is also 0. I can change this value to whatever I want by editing it in the kernel editor. So let's make this one 48. And let's make this one quite a big number. So we'll make the ones on the edges maybe, let's make them 20. This has changed the shape of my kernel quite a bit, and in fact is no longer a Gaussian kernel. But this is a demonstration of how quickly you can create and edit your own kernels in RAMP. Once you're happy with this, I'm going to change the name of this. It's going to be called Special Kernel. I can save this now, save as, and I'm going to save it to this file called Special Kernel. So now I have my special RAMP kernel that I've just added in here available to me so that I can use it again. The neat thing about RAMP that's different from other kernel processors is that, in fact, the kernel doesn't have to be square. It's defined initially as being square, but it doesn't have to be square. So I can, for example, delete this and I will have null values in my kernel. So these don't apply or aren't even shown in the kernel themselves. So let's take a chunk of the corner of this kernel out by simply specifying nothing. So now I have a non-square, let's do a bit more. I now have a non-square kernel. Why is this useful? Well, it allows me to specify any shape in reality. So in this case, the kernel is predominantly operating in a sort of southwest northeast direction, and that's important if you have data that is anisotropically biased, for example, or directionally biased. So that's a unique thing about RAMP, is that you can have non-square kernels that are of any shape. And in fact, if I wanted to, I could have holes in my kernel as well. So in this case, I'm going to put a hole right in the middle. So this is a really interesting property of RAMP that's not available in other image processing software. I'm going to save this so we can maybe play around with it later. So let's jump into the kernel processor itself. I'm going to double click on it here, and the processor will open, and you'll notice that there's one method within this kernel within this processor called apply kernel filtering. And what it expects is a input raster and a kernel definition file, and we've seen these kernel definition files in RAMP, and in fact our special kernel is available to us now here as well. So we need to get an input raster first. Let's do that. I'm going to load this data set, and I'm going to render it. And this is kind of what it looks like. I'm going to just EQ it so that it's a bit easier to see. This is a terrain data set that shows a mound, and on top of the mound are these sort of pimple-like features. They're pock marks at the top of this mound. And so I might want to use, say, edge detection to really highlight where these pockmark features are in the image. So let's have a look at how we might do that. I'm going to launch the kernel processor, apply kernel filtering method, choose my input raster, and I'm going to use, say, a 3x3 edge detector. And click OK. And it's processed that. I'm going to render it. Let's make this grayscale. Where's my favorite grayscale? Here we go. I'm going to render it so it stretches to 1 standard deviation. And you'll note it's starting to really pop out where those pock marks are in this image. Let's try a different kernel now. So I'm going to choose the 9x9 Laplacian of Gaussian kernel. The Laplacian of Gaussian kernel is also a really good edge detector. So let's have a look at how that works. Okay, and let's try to render it the same way as the other filter that we applied. There you go. This is the Laplacian of Gaussian kernel applied to the terrain data set. Looks like the colors are inverted, so let's just reverse those. And now you can see the difference between the 3x3 edge detector and the 9x9 Laplacian of Gaussian, and it's really starting to show these pockmark fields in the image, and it really helps me be able to provide some interpretation of where these features are occurring. There's some rocky sort of outcrops on the downslope of this mound that also really stand out once I've applied my edge detection to the imagery. For fun, let's see what our special kernel did. So let's just go back to the kernel editor and have a look at what that looked like again to remind ourselves. We created a non-square kernel with a null value in the middle. I wonder what that's going to look like once we apply it to this image. So let's give it a go. Okay, let's hope this works. Okay, that's interesting. Let's render it in the same way. And we can really see the directionality that we added to this kernel and how that sort of manifested in this image. Probably not very useful in this case, but nonetheless an interesting outcome. So that's a quick introduction to kernel processing and RAP. I hope you found the video useful.